Instead of sharing the screen, I cut the recording. Not a very good idea. Okay. So you see, so if I just use these three equations, and I take u equal, let's start with u equals 4, for example, here. This is the charge structure factor on the left and the spin structure factor. So what is the charge structure factor? It is just it's just the Fourier transform of Sz of R Sz at this, that's the spin structure factor. So Fourier transform. In other words, this is like
I can't really see your equations right now because you're sharing your screen.
Ah, yes. Okay, good point. Let me unshare the screen. I'm saying that the spin structure factor is this Fourier transform of this. So it's this. So it's at the same time. Okay. So it just means integrated over, summed over Matsubara frequencies. Okay. So if I share the screen again. So on the right is the spin structure factor, and on the left is the charge structure factor. This is u equals 4 here, u equals 4. And so this is different fillings. You see 0.30, 0.19, 0.33, 0.8. And the dots are the results of Monte Carlo calculation. So in other words, they are exact within statistical accuracy, but you can improve the accuracy as much as you want. So you should consider the dots here like an exact result for an 8 by 8 lattice, but the temperature is sufficiently high that there's no finite size effect. Temperature here is 0.5 times hopping. And the solid lines are the results of this, solving these little three equations. Okay, so you see that for the spin and the charge, it works really well. And for the charge here, it's not even monotonic in the sense that if I take n equals 0.26, I get this. N equals 0.6, I get this, the green curve. And n equals 0.94, I get the red curve. So we see it's not even monotonic. And okay, and then for u equals 8, it doesn't work as well. But indeed, this theory is good just in the weak to intermediate coupling, which means that when u is of order of the bandwidth or a little bit less, the approach fails. In other words, there's no Mott transition in this approach. Or it's all based on quasi-particles in that sense, and just sort of seeing the quasi-particles disappear, but just at the limit. Okay. So okay, so it's worth the effort. In other words, that's what I'm saying. Works pretty well. Now, why is it that it's not monotonic? It's because you see, when we add these two equations, we saw that an up and down disappear. So the right-hand side is a constant. I got everything backwards there. So this is the charge. And this is the spin. Oh my God. Spin and charge. Right? That is a charge and that's a spin. So if I add these two equations, this disappears. So the right-hand side is independent of interactions. Depends on filling, but monotonically. So you see that when the spin fluctuations increase here, it means that the charge fluctuations must decrease to compensate. So that's why it was not monotonic. Okay. So now I think I can get rid of this. And I show you how we get this. Okay. What do we have for the self-energy? We have that sigma of 1 bar, G 1 bar, 2 sigma. That's the piece that came from commuting the field operator with the interaction part of the Hamiltonian. So it means that on the right-hand side, we have U, and we have psi dagger minus sigma 1 plus psi minus sigma 1, psi sigma 1, and then psi dagger sigma 2. So when we did the commutation relation, we got rid of the psi dagger, and we got these three field operators. And then when we put the psi dagger 2 to the right hand side to get a Green's function. So that's how we get this. Okay. So so that's exact here. So now we have to do some approximation. So let me. So in Hartree-Fock is equivalent to factoring these two objects, right? Hartree-Fock was saying, okay, I will write this as minus U, and I will write G of 1 plus 1, and then this I need to put this in the right side. It's plus G of, and that's minus sigma, and that's sigma G of 1, 2. Okay, so this is in the right order, but that's the wrong order, so that's why I changed the sign there. And then when you multiply by G minus 1, you have the usual result that sigma is U times G minus sigma. That was the Hartree-Fock approximation. But now, what happens if I look at 2 equals 1 plus? So I take sigma of 1, 2, 1, 1 bar. G of 1 bar, 1 plus. Okay, now what do I have? Then this 2 is equal to 1 plus, so I have to put it on this side. That will get rid of the minus sign, and that's equal to U times n down and n sigma, so n minus sigma n sigma 1. Okay, and we have seen this type of equality before, and I will use it again later in this integral accuracy. So you see, this is very important because this, if you want, we know when the two spins are identical, we know the result by the Pauli principle. It's just and up sigma and up is equal to n up squared is equal to n up. But this function we don't know, and it's an important one. It's double occupancy. So what we will do then is to say, okay, when this point 2 is not at the same point 1, the correlations are lost. So I can separate here the propagation in this way. But then here I will replace u by some constant a. Everything is a function of phi. We're still working with functionals there. So I will replace by a constant a in such a way that when 2 is equal to 1 plus, this equation is satisfied. Okay. So how do I choose a? Well, it's easy. What I choose for a will be equal to n minus sigma n sigma times u. So that's this. Divided by this when 2 is equal to 1 plus. But when 2 is equal to 1 plus, what is this? This g of 1 plus 1 is the expectation value of n minus sigma. And this g of 1, 2 plus, when 2 is equal to 1 plus, is n sigma. Okay, so you see it starts to look like this. So now that I have the self-energy, okay, the self-energy, I get it now by multiplying by g minus 1, right? So if I want to have the self-energy of 1, 2, I multiply by g minus 1, so that becomes delta of 1 minus 2. And now I can compute for example, the spin vertex here. So you see, I need to differentiate sigma down with respect to g up, or if you want, sigma up with respect to g down, right? So I will this will disappear. And then I need to compute this also. I'm sorry. So that's not the only contribution. When I take this functional derivative, this disappears. But this a here is still a functional of g, because we're always working with these everything here is a function of this phi, or indirectly is a function of g. Phi. So if I take a functional derivative of a with respect to again to the let's say I have sigma up, which is compared with functional derivative with g down. Okay, this will give some contribution that's complicated, but the happy result is that when I take this term here, there's a minus sign. And when I take this term, nothing comes from this, because the spins are different, and this is for the same spin. But the contribution that comes from the functional derivative of this is precisely the same as the one that comes with the functional derivative of this. Why? Because you see, this is completely independent of spin up or down. Okay, it has minus sigma, sigma, and minus sigma, sigma. So if I take the functional derivative of this with respect to g up, it will be equal to the functional derivative, the same thing with respect to g down. Okay. So when I take the functional derivative of this, it disappears. So the only one that survives is this. So it means that U spin is equal to A basically, which is this quantity. Okay. Now when I compute U charge here, I have a plus sign. So these two functional derivatives cannot cancel. So U charge will be something complicated. But I say, okay, let's use the Pauli principle, and then we will have U charge as well. Okay, so that's an extra hypothesis if you want. So to fix the Pauli principle, we say that U charge is determined by the Pauli principle, basically. But U spin gives us this, this and that. Okay, so you see it's very simple. And it gives these nice results that I showed you. Okay, any question? So I'm going to jump ahead a little bit and show you why it satisfies the Mermin Wagner theorem. Before I go to this, why it satisfies the Mermin Wagner theorem and what is this Kanamori-Brueckner screening. So Mermin Wagner theorem. So we have this T over N, sum over I Q N, sum over Q of chi 0 divided by 1 minus U spin over 2 chi 0 is equal to N minus 2 and up and down. Now remember that the chi 0 is this. Chi 0 is equal to integral d omega prime over pi of chi double prime for omega divided by omega minus I Qn. And this is odd, remember, because of dissipation needs to be positive. So this is equal to integral d omega prime over 2 pi. I multiply by a complex conjugate, numerator and denominator. So that's chi double prime of omega prime times omega prime square plus Qn square. Okay, I just multiply by complex conjugate, numerator and denominator. And because this is odd, then the term that's in front of IQN vanishes when I integrate over frequency. So why did I do this? Well, because I just want to show you that this function, as a function of IQN, you see the numerator is positive. So it means that if you plot this function as a function of Qn, of the Matsubara frequency, it's just decreasing, right? And it has the largest value at Qn equals 0. So if there is a phase transition, it comes from the fact that this denominator becomes infinite. And why will it become infinite? It can become infinite only at Qn equals 0. So let's focus just on this quantity then at Qn equals 0. Then what we will do is we see that 1 minus u spin of over 2 times chi 0 of the q 0. There will be a wave vector q where this will be, eventually this would vanish if there was a phase transition. So let us expand in powers of q. Okay, let's call big Q the wave vector where this function is a maximum. Then it means that if I look at the first order in little q minus q, I do a Taylor series. The first order in q minus q will vanish because by hypothesis, this chi 0 is maximum at big Q, which means that the first derivative cancels. Okay. So I just have the second derivative. So the second derivative, I will have minus u spin over 2 times 1/2 d square chi 0 evaluated at q. I need to, at 0 and dq square times q minus big Q square. Okay, so this will vanish, but this is sort of, the next term that will be different from 0. I have to do this integral. Okay, so let us focus on the term qn equals 0, like I said. All the other terms will give me some finite contributions. Okay, so I will put to the right here. So I combine this thing with everything that was all the qn that were at finite frequency. And I call this would be a function of temperature, but it's not divergent. I mean, the divergence comes from doing this this integral. Okay, so I can do the same expansion in the numerator, but what's important is really what's happening in this denominator. So the sum over q divided by n, this becomes integral d squared q over 2 pi squared. And this, then this becomes some constant, that's chi 0 evaluated at q. And now I will switch the order, the origin of integration so that it's around big Q, okay? So it means there that I will have a term that will be c minus 2 plus q squared. Okay, so so you see what happens is that this term, and now this derivative here, and because this is a maximum at big Q, means that the second derivative is negative. So this whole thing is a positive number. So I can just factor this and put this with the numerator. So that's this constant to a. And then this guy divided by this is what I call c minus 2, because this has units of wave vector, and this I call it will be have units of the inverse of a length. Okay, so that's a so-called Ornstein-Zernicke form. Okay, and then this is equal to some constant c. I'm sloppy here. I understand I'm sloppy, but the idea is that I just want to show that this integral does not diverge. Okay, I'm not doing anything quantitatively. Are you uneasy with this, or is it okay? Do I have permission to continue? Okay. So I expand this around. So I take the 0 Matsubara frequencies. All the other ones, they give a finite contribution. I put them to the right. And then I expand the denominator around the place that's going to vanish. And then I can factor this thing and compensate with the numerator. So that gives me some constant in the numerator. And the denominator has this q square and this c minus 2, which when c goes to infinity, and that's what happens at the phase transition, second order phase transition, this guy goes to 0. Okay. So what happens then? Okay, then if I continue to be sloppy here, you see that this is this d squared q is just q dq, and I have q squared. So the integral is a log basically, right? So I get t that times a log, so that can be a function of t times the log of c over some cutoff, some lambda, some cutoff. So it means that it means that c goes like exponential of c of t over t. Okay, so it does become infinite. So there is a phase transition. When this c is infinite, this is 0, and that corresponds to the phase transition. But you see it occurs at 0 temperature. So it satisfies the Mermin Wagner theorem. Okay. Okay, now another interesting piece of, is there any question? Okay, another interesting piece of physics now. Let's go back to what we had before. Let's suppose I am far from a phase transition now. If I'm far from a phase transition, in other words, this is small, I can expand this. So I get t over n, sum over iqn, sum over q of chi 0, and I get 1 plus u spin over 2 chi 0 equal to n minus, okay, and this, what is this? This is u spin over u times and up and down. Okay, and there's a 2 here. So now I can solve for u spin, you see. I can solve for u spin easily. And I'm not going to waste some time here because it's really just some algebraic equation. And you get, the final result would be that u spin is equal to u divided by 1 plus u times some number where lambda is equal to t over n sum over iqn sum over Q of chi0 square divided by n square. So perhaps I got this wrong. In fact, I'm just doing from memory. But what's important is you see that you can clearly solve for U spin, right? So this will be chi0 square. So that's why I get this chi0 square in the numerator. So the interesting piece of physics here is that when U is very small, then U spin is U. But as U grows, then U spin starts to saturate. And what is the physics of this? The physics of this is the physics of Kanamori and Brueckner. So Kanamori was a solid state physics and Brueckner was a nuclear physics. So what is happening with this Kanamori-Brueckner screening is that if you have two particles that scatter off each other, or a particle and a whole, then you say they scatter only once, then this is the Born approximation for scattering. But you know what will happen if you look at scattering theory? You have a plane wave that's incident, and the wave that's going out is composed of spherical waves, and the wave rearranges according to the potential. In other words, if the interaction is very strong here, the two-body wave function will want to have a cusp here. So if let's say you have U on a site, and you have a U on one of the orbitals here that's very large, then the two-body wave function does not want to feel that U. So it does this, and that costs kinetic energy. But in a system where the kinetic energy is finite, because you have one band only, means that the most that it can cost is the bandwidth. So that's why when U is very large, then U spin saturates. And it's so in terms of diagrams, it's because you have to sum the whole Born series. Here it does not come out so clearly as diagrams, but in the end, that's what happens. So if you solve these equations numerically, the equations for the spin and the charge, like I showed, then the final result, and you see both of these effects. I will show you. I don't think I put that plot in the lecture notes. I should have done that. I will do that eventually. So what happens is that if I draw this SZ at the most divergent wave vector, which turns out to be pi pi if you are at half filling. So I take the model with only Hubbard model with only nearest neighbor hopping, and I take n equals 1. Then it is the pi pi wave vector that will be divergent. This I have not shown, but I will discuss this a little bit later. So if you plot this as a function of temperature, what you find is that around for u equals 4, for example, is around a temperature that's about 0.2 in units of little t. The correlation length, I mean, this quantity starts to grow a lot. We know that it will diverge exponentially, so it starts very quickly. And then if we do RPA with the same theory, then what you find with RPA is that around 0.75. So it's quite a bit, let's see, 25 here if you want. So it's like 3 times larger. Then in RPA, there's a phase transition. Okay. So you see that here it's not a real phase transition, but it starts to grow exponentially. And instead of starting to grow very quickly around 0.75, it starts to grow around 0.25. And the reason is because of this screening. I mean, the fact that U spin is not equal to the bare U. Okay. So there are 2 elements of the physics that we are getting here, which is this sort of nuclear matter or Kanamori-Brueckner screening, which has to do with the self-consistent rearrangement of the wave function, such that the effective U is smaller than what you would have thought. So it's sort of renormalized by the, if we call this particle-particle scattering another channel. So it's renormalized by other channels. It turns out that here it looks like another particle hole channel, but anyway, it's renormalized by quantum fluctuations, if you want. And then this is, then you get this increase here. So this regime here at very low temperature, what happens is that the characteristic spin fluctuation frequency, so omega spin. So if I draw, let me draw chi double prime. Spin at this wave vector as a function of frequency now. So it vanishes at omega equals 0. So it has it has a structure like this. And it has a peak here at what one can call omega spin. So in this regime where the correlation length is very large, omega spin becomes much less. So h bar omega spin, if you want, becomes much less than kBt. So it's as if we have a new classical regime. You remember the harmonic oscillator? With the harmonic oscillator, you reach the classical regime when kBt is larger than the separation between levels. So this regime here we call renormalized classical. Because you see you have quantum fluctuations here, you have lots of quantum, you're in sort of a quantum regime at very, very high temperature, larger than the Fermi energy or a classical regime. And then you get a new classical regime, which is renormalized classical in the sense that the characteristic spin fluctuation frequencies are less than temperature. Okay. So are there any questions? Okay, so next time we will do, so what I've done now is I've sort of skipped this, and I went to the more physical aspects of this, more physically interesting results of all of this that don't need this, this sigma 2. Just you know, on the spin fluctuations, we already have lots of physics to discuss. So next time I will show you that we get better approximation for the self-energy. You see, the self-energy that we got was basically the same as R3 Fock, but with U spin instead of U. So it means that the chi0 that we can call chi1, if you want the first level of approximation, is really like a bare chi0. I mean, if you want, the self-energies are constant. It's not the same constant as R3 Fock. So we don't, but you can put that in the chemical potential. I mean, it's just a constant. So basically the chi0 is the same as the non-interacting one. But then we will move to a better approximation for sigma 2 here. Okay? Any questions? Okay. So we'll see you on Friday then.
Bye-bye, merci.
Bye-bye. I'll stick around if you have some questions you want to ask in private.
Thank you.
Thank you. Bye-bye.
Okay.
Thanks. Bye.